Welcome. This question says a 2 kilogram particle with a velocity of plus 5 meters per second collides elastically with a 4 kilogram particle that has a velocity of minus 3 meters per second. And the question is, what is the velocity of the 2 kilogram particle after the collision? So if we visualize, we have a 2 kilogram particle and it's traveling to the right at plus 5 meters per second, and it's going to collide with a 4 kilogram particle which is traveling to the left with a velocity of minus 3 meters per second. They don't stick together. It's not a perfectly inelastic collision. It's an elastic collision, so they don't stick together, but we don't know either of these two values. So I'm going to call that V1 and I'm going to call this one V2, if you like, V1 final and V2 final. So it's elastic. It means that not only is momentum of the system before and equal to the momentum of the system afterwards, not only is momentum conserved, but the kinetic energy of the system before is equal to the kinetic energy of the system afterwards. So I have two equations, and so I can have two unknowns, and there's one unknown and there's the second unknown. So let's begin by applying the conservation of momentum law. The momentum of the system initially is equal to the momentum of the system final. So it's going to be m times v, so it's going to be 2 times plus 5, that's the momentum of the first particle, plus m times v, which is 4 times minus 3, that's the momentum of the second particle, is equal to, and it's going to be m times v, 2 times v1 final, plus 4 times v2 final. Well, this is going to be 10, and this is going to be minus 12, is equal to 2v1 final plus 4v2 final, so minus 2. Minus 2 is equal to 2v1 final plus 4v2 final. So we have an equation that we can work with. Now let's think about conservation of kinetic energy. And frankly, if I try to do this problem using a half mv squared for the first particle plus a half mv squared for the second particle is equal to a half mv squared for the first particle after the collision plus a half mv squared for the second particle after the collision, it makes it mathematically quite arduous. And then somebody came along with a really clever equation, and what it says is that the difference between the initial velocities, so that would be v1 initial minus v2 initial, the difference between the initial velocities is equal to the negative of the difference between the final velocities, so v1 final minus v2 final. It's a very simple expression. It's a correct expression. It's not an obvious expression that you would just know. So if we put real numbers in for this, we say, well, plus 5 minus 3 is equal to, and we have that minus and that minus making a plus, so let's just rearrange this, v2 final minus v1 final. So I simply say, oh, 8 plus 8 is equal to v2 final minus v1 final. And so I have what I need when you have two unknowns in a question. You need two equations, and so I have the two equations. So I need to isolate in one equation and then substitute in the other equation. And the trick is, and this is where people sometimes, they go around the houses to find the answer. It's asking me what is the velocity of the 2 kilogram particle after the collision. The 2 kilogram particle after the collision. And the 2 kilogram particle is here. And so the velocity I want is v1 final. That's what I want to end up with. And so what I do is I isolate. Let's just take this first equation. And rather than isolating for v1 final in this first equation, I'm going to isolate for v2 final. So I'm going to say, well, if minus 2 is equal to 2v1 final plus 4v2 final, I deliberately isolate for v2 final. So I can say, oh, minus 2 minus 2v1 final over 4 is equal to v2 final. So I rearranged my first equation to get v2 final by itself. And then what I do is I take that and I take this equation here and I say, well, that means that plus 8 is equal to, well, if it's equal to v2 final minus v1 final, well, plus 8 is equal to, I know what a v2 final is, minus 2 over 4 minus 2 over 4 v1 final minus v1 final. So I need to do a little bit of a rearrangement here. So I have 8. This is a half. It's negative. So I'm going to say plus 1/2 is equal to, and this is minus 1/2, and that's minus 1, is minus 3 over 2 v1 final. So that would be 16, 17 over 2 is equal to minus 3 over 2 v1 final, final little step. v1 final is equal to, well, the 2's cancel each other out, minus 17 over 3. v1 final is equal to minus 5.67 meters per second. So there's my answer. And, well, 5.66 is that. So there we have it. It's takes several steps. First of all, recognize that it is an elastic collision. And so I know that not only is momentum conserved, but also kinetic energy is conserved. Then you suspect you're going to need 2 equations because you have 2 unknowns. You visualize, and sure enough, you don't know what the final velocity for v1 is, for the first mass is, and you don't know what the final velocity for the second mass is. 2 unknowns. You apply conservation of momentum to get your first equation. You apply not conservation of kinetic energy. There's a new, not obvious equation which says the difference between the velocities before the collision is equal to the negative of the difference between the velocities after the collision. And I apply that equation and I get my second equation. And then the little math trick, the thing that can save you time, is you recognize that if you want v1 final, I take either one of these 2 equations and I isolate the other thing, v2 final. And then I substitute that into the second equation. And so my second equation is now only in terms of what I want, which is v1 final. And the math sorts itself out. If I'd not realized that, I would have got a solution for v2 final, and I would have had to substitute back into either one of the 2 original equations to get the answer that I want. And there we have it.